In this video, I'm going to talk about transformers. Transformer is a static device. Transformer is a static device which transfer electrical energy from one circuit to another circuit without changing the frequency. That's the main purpose of a transformer. Okay, there are three important electrical missions. The first one is generator, which converts mechanical energy into electrical energy. Another one is motor, which converts electrical energy to mechanical energy. Third one is transformer, which converts electrical to electrical. It is not going to convert AC to DC or DC to AC. We will give AC input, it will give you out AC output. Okay, if you give DC input to a transformer, it's going to damage the equipment, so never ever connect a DC. I will talk about it at the end of this video. There are mainly three important parts in the transformer. One is called core. The main iron piece is called the core. So here is the core. All this is core. Another one is a primary winding. This is primary winding. This is secondary winding. Those are the three main important parts of the transformer. Now I'm going to talk about why do we need a transformer, since it is converting electrical energy to electrical energy. So here is a simple system I'm going to take. Assume here is a load center. This load is taking a 10 megawatt of energy power, 60 hertz frequency, 10 kV system. Usually voltages are 11 kV, 13.3 kV. I'm just taking this for calculation purpose, okay, to make it easier. I'm also assuming the power factor is unity power factor load. Now I'm assuming this is a single phase. It's just a calculation purpose. Most probably you will say three-phase system. Now assume that here is a generator. This generator also utility company or power plant, which is like 10 miles away from the load. So you have to run a transmission line. Okay, here I'm assuming it's a single phase transmission line. Now every wire will have some resistance. That resistance R equal to rho L by A. Rho is the resistivity. So what kind of wire we are using? Copper wire, aluminum wire, something like that. L is length of the wire. A is cross-sectional area of the wire. For time being, I'm assuming that resistance is 1 ohm. Okay. So if I take it for time being, I'm going to take it as 1 ohm total resistance. Now, what is the current what is the current flowing through this wire? I equal to P over V cos theta. Here cos theta is 1, so I didn't include the cos theta. 10 megawatt divided by 10 kilovolt, I end up with 1000 amperes. So the current passing through this is 1000 amperes. Now 1000 square times R line is 1 ohm, so 1000 square times 1, it's 1 megawatt. So we are wasting a 1 megawatt of power in the transmission system to supply 10 megawatts. So it's approximately 10%. 10% is a very significant amount of energy loss. So the utility company has to generate 11 megawatt. So you are paying only for 10 megawatts of power. That's what you are using. But power company has to supply 11 megawatt. So, and it is also wasting 1 megawatt of power in the transmission system. So it is wasting the fuel, whatever it is, either coal or nuclear or hydro, whatever it is. So it is wasting that fuel. To supply 10 megawatt of power, it is generating 11 megawatt of power. Now, to minimize the losses, what I'm going to do, I'm going to introduce a transformer. So here is the same system, 10 megawatt of load, 60 hertz frequency, 10 kilowatt, 10 kV line, and power factor is unity. So what I'm doing here, I'm using two ideal transformers. So usually transformer we indicate with two coils. If you see these lines in the middle, that indicates that that's ideal transformer. So here the first transformer, I keep it very close to the generator. Second transformer, keep it very close to the load center. Okay, so first transformer is a 10 kV. If I give the 10 kV input, it is changing it to 100 kV. We call that as step-up transformer. And another one is 100 kV. We give the 100 kV voltage, and and it is giving you back 10 kV voltage. Step down transformer. I'll talk about step up, step down in a minute after this. Now, what is the voltage here? Voltage in the transmission line is 100 kV. Now, what is the current passing through it? 10 mega over 100 kV. The current passing through the line is 100 ampere. Now, what are the power losses? I square times RL, which is 10 kilowatt, okay, which is 0.01 megawatt. See, previous case, the power plant has to generate 11 megawatt. Now, in this case, it has to generate only 10.01 megawatt. So, we reduced the transmission line losses a lot by using a transformer. That's the main advantage of a transformer. We can transmit energy for longer distances with minimum losses. That is the main purpose of a transformer. Now, I'm going to talk about ideal transformer. We understand what is the purpose of a transformer, right? Now I'm going to talk ideal transformer. So here is a transformer, ideal transformer. We have primary winding. This is called primary winding. And so primary winding is which is connected to the source. And secondary winding, we call this as secondary winding, which is connected to the load. Okay, secondary. Okay, now you can see it here, primary winding and secondary winding. Input is connected to the primary and output is connected to the secondary. N1, we call that as primary number of turns. N2 is secondary number of turns. V1 primary supply voltage, V2 secondary terminal voltage. I1 is the current flowing through the primary winding, I2 is current flowing in the secondary winding. E1 induced EMF in primary, E2 induced EMFs in secondary. So here this is a V1, number of turns on the primary, number of turns on the secondary, and induced EMF here E1, induced EMF here E2. So for ideal case, ideal transformer, V1 equal to E1. Okay, there are no losses. So whatever the supply voltage is appear across the inductor. Same thing, E2 equal to V2. V2 is right here. And here is I1, here is I2. So there are two types of transformers. One is step-up transformer. Step-up means your V2 is, step-up transformer is V2 greater than V1. And step-down is V1 greater than V2. Okay. Now, I always, when I was a student, I always get this said, by using transformer, can we supply energy to the to a home for all 24 hours? Because I'm from India. I'm from a small village in India. I moved to US like 17-18 years ago. At that time, we used to get only energy for a few hours, like 10 hours, 12 hours, something like that. Because there are not many power plants at that time. Now I think they're supplying more than 20 hours a day nowadays. But it used to be only 5-6 hours or 10 hours a day. Now, when I was a student, I used to think, okay, why can't we use more number of transformers and supply energy for 24 hours? Because we can step it up and step it down. Okay, remember one thing, we are stepping up. Remember one thing, we cannot create energy or we cannot destroy energy. Okay, so whatever energy we are giving, we will get the same amount of energy or little less amount of energy. The transformer, in real transformer, is around 95% efficient. So if I give 100 watt here, it will give you only 95 watt. Okay, but in this case, I'm taking ideal case. So if I give 100 watts here, you will get 100 watts there in ideal case. Okay, so the power is same. P equal to V1 I1 cos theta. For time being, I'm going to take this as cos theta as 1 and V2 I2. So what I'm saying, my P1 equal to V1 I1, P2 equal to V2 I2. Okay, and P1 equal to P2, so definitely V1 I1 equal to V2 I2. So V2 over V1 equal to 1 over I2. That's the relation. So this indicates that whenever I step up, so here I'm giving 100 volt, 100 P1, and say V1 is 10 volt. Okay, now what is the current? Current must be 10 ampere. Now P2, same power, 100 watt. Now I'm stepping it up to 100 volt. What happens to the current? Current is going down. Okay, so a step up transformer steps up the voltage, steps down the current, and power is going to be the same. Ideal case, power on the primary side and secondary side is going to be the same. Okay, that's what we need to understand. And another thing is we're going to find the relation between N1 and N2. So V is nothing but, or V1 equal to E1 equal to N1 times d phi by dt, rate of change of magnetic field. So V1 is proportional to N1, and same way V2 equal to E2 equal to N2 over d phi by dt. This d phi by dt, they both of them are same, so I can write down V2 over V1 equal to N2 over N1. This is called transformer ratio. Okay, transformer ratio I indicate with the K or N. Some books uses K, some books uses N. Okay, another term you need to know which is, so the transformer ratio K equal to N equal to V2 over V1 equal to N2 over N1 equal to I1 over I2. Okay, in this class I used K for coupling coefficient, so to avoid confusion, let me take this as N. Okay, N is transformer ratio. There is another term called A. This is called turns ratio. This is called transformer ratio. Okay, N is transformer ratio, A is turns ratio, which is V1 over V2 equal to N1 over N2 equal to I2 over I1. So basically N is nothing but 1 over A. Okay, both of them are same. Okay, so in this video we learned about basics about transformer and types of transformers and the relation between the input and output voltages and current. So another important thing, never ever connect a DC to a transformer. Okay, never supply DC voltage to a transformer, since there won't be any change in current, there won't be any change in magnetic flux. So basically if this I1 is not changing, what happens? This inductor, if I supply DC, the inductor is going to act like a short circuit once it is fully energized, right? So there won't be any change in the magnetic field. It will produce the constant magnetic field. So that's a constant magnetic flux when it is passing through this cross-sectional area. So the flux, there is no rate of change of magnetic flux. There won't be any induced EMF across this coil. So E2 is going to be 0. So this will act like a short circuit and lots of current is going to pass through the transformer. It will damage the transformer. So never ever connect a DC supply to a transformer. I'll stop this video here. I'll continue examples in the next video. Thank you.